So there was a question, maybe I should add one more thing to what I said about terminal objects. There is nothing I said about outgoing arrows from the terminal object. I talked about incoming arrows to the terminal object. They have to be unique from every object, right? It doesn't mean that there are no outgoing arrows, and in fact, there are usually outgoing arrows from the terminal object, and these are the arrows that help us define these generalized elements in other objects. Right? Every arrow from a terminal object to another object is a definition of a generalized element in this other object. Because this is what happens in sets. When you map a singleton set into some other set, that's equivalent of picking one element and saying this element of the singleton set is mapped into this particular element of the other set. So it's picking an element. There are many morphisms. Each of them picks a different element, right? So you can generalize it to any category and say, if I have a terminal object in my category, then a morphism from terminal object to any other object is sort of like picking an element, right? I don't know really what an element is. This is as close as I can come to saying this is a generalized element of some other stuff, okay? And this is why it's important, because like if you want to have a category that sort of is like set category, because there is a bunch of categories that have similar properties as the category of sets, you know. So there are certain things that you would like to have in them, and one of these things is being able to having a terminal object, because a terminal object gives you this way of picking elements. Okay. Okay. So now let's talk. We have now two examples of universal constructions: the terminal object and the initial object. And I was kind of talking a lot about the terminal object, right? But when I was talking about the initial object, I was sort of like just waving my hand, saying, "Well, you do the same thing as with the terminal object, just reverse the arrows, right?" It's like a lot of the stuff is just boring stuff, right? Because it just happens when you reverse the arrows, you get the other one. So it turns out that this trick with reversing arrows actually has a much deeper meaning. Okay? Every construction in category theory actually has its opposite construction that is done by reversing arrows. So if you define terminal object, you know, you get for free the definition of the initial object by just repeating the same thing but with inverted arrows. And this property is related to the fact that for any category, you can always create a new category which is identical to the other category, but with all the arrows reversed, right? So you have a category C, right? You have some objects A, B, and you have an arrow from A to B, and so on. There's an example, right? The opposite category, it's called C-op, usually, is obtained from this category. It has the same object, so we have the same A, the same B, and if this was F, right, this arrow is called F, we have an arrow going in the opposite direction. We call it F-op. Okay? So so to every arrow F here, from A to B, there is an arrow F-op going from B to A. Right? Now, how do we know this is a category? Wait a moment. right? I said just this is a category. Is this a category?
Maybe if we had another object we could track it close enough.
Right, so we have to think about composition, right? So what happens if I have an object C and some G here, right? Yeah, let me make this category a little bigger. So we have an object C. Now the opposite of G will go this way. The composition of G after F goes this way from A to C, right? Now if I map this stuff to the opposite category, I will have G after F up, right? So this arrow is mapped to this arrow that goes from C to A. So the trick is that when I reverse all the arrows, I also have to reverse the direction of composition, right? So G after F up is a composition of F up after G up, right? Because the end of G up is B, the beginning of F up is B. I can compose them, right? And I get this one. So, but notice that this was G after F, this is F up after G up. So I have inverted the order. But other than that, it's a perfectly good category. I mean, associativity is automatic here. What happens to identity? Well, the identity, when you invert the identity, you get the identity again, right? So that's kind of tricky. Okay. So for every category, you have the opposite category, and in this opposite category, the arrows go the opposite way, right? And this is a very useful thing. So instead of me saying, oh, let's now define initial object, I could have just said, initial object is defined as the terminal object in the opposite category, right? That's it. Because in the opposite category, the arrows go the opposite way. And the terminal object in the opposite category will be this guy, right? And this is an initial object in this category. So there are a lot of constructions like this, right? Where you just say, well, now let's go to the opposite category, and that's it. And I usually will actually describe in more detail what happens in the opposite category because it's an interesting construction. It doesn't mean it's trivial, you know. I mean, the difference between a terminal object and an initial object is huge, right? It's an empty set and a singleton set. They have completely different properties. So continuing this story of this ancient civilization that knew set theory and then they forgot everything about it and now they have category theory and only know about arrows and stuff, right? They discover one day that the ancients had something called Cartesian Product, okay? And what was it? You know? So, in Cartesian Product, in terms of elements, they knew that, the ancients, but they never wrote it down, so we don't know about it. But what they were thinking is that a Cartesian product of two sets, right? It's like you have one set A and another set B, you know? You take an element from one set and an element from the other set and you form a pair, E1, E2. And the set of all these pairs is called the Cartesian product of these two, right? And we have examples of Cartesian products. For instance, a plane is a Cartesian product of two axes, right? So we have the x's from one axis and the y's from another one, and the pair xy corresponds to a point in the axis. So I often will be drawing stuff like, this is one object, this is another object, this is a Cartesian product, right? Because in a sense you have this, right? A point in a Cartesian product corresponds to a pair of points from the objects. But we have already forgotten about this stuff, and now we are reading these ancient scrolls, and they say this Cartesian product has some properties, right, that are expressed in terms of arrows, functions, right? Like what are the properties of the Cartesian product that we can express in terms of functions? What there are, for every Cartesian product of two sets, there are these two special functions called projections, okay? And in a programming language like in Haskell, we call them first, FSD, and SND, second, okay? So the ancients told us that there are this for every Cartesian product, of A cross B, there are these two arrows called first and second. This one maps it to A, and this one maps it to B. Well, actually, I should draw this as a point, because now we are in category. I don't even know. This is like an object, right? And this is an object called A cross B. And I just know that there are these arrows, okay? That's all we know. It's like anything can be called a Cartesian product. I mean, that's a pattern here, right? We have two sets, A and B, or two objects, A and B. And we have an object that pretends to be, I'll just call it C now, because I don't know if this is a Cartesian product or not, right? I think it might be a Cartesian product. All I know is it has these two functions. Well, maybe I'll call them P and Q, okay? And I'm saying, okay, I have this pattern. I mean, A and B are fixed, right? But the pattern is, pick an object C that has two arrows, one going to A, one going to B, right? So this is my pattern. Maybe I should change the color, and I'll draw this in black, because this is fixed part of the pattern, right? The other part is flexible, right? So, do I have another color? Okay, so there could be many such things, because I don't know anything else about this pattern other than it's an object and two arrows going to A and B. It could be anything, right? Now, one of them is my Cartesian product, but which one? Right? I have lots of these guys. So it's like C1, C2, P1, P2, and so on. I have lots of these. And if I could look inside, I would know, oh, this is my Cartesian product, because it's just the pairs, right? But if I can't look inside, how do I know which one is the correct one? And of course, the universal construction to the rescue. I have to be able to rank them. I have to be able to say, this candidate for a Cartesian product is better than another candidate. So, how do we rank these things? So let's say we have C and C prime. So this is P and Q. These are the two morphisms, P and Q. These two projections, let's call them projections. And this is P prime, and this is Q prime. Okay? And we are comparing these. We are saying that C is better than C prime if there is a morphism. Let's call it M, from C prime to C. Okay? So this is sort of similar to what we did with ranking for the terminal object and the initial object. Let's just say that there is a morphism that maps them, right? So there is an arrow between them, right? And just like previously, we impose the condition that this arrow is unique, okay? So a unique arrow from C prime to C. Is this enough to pick the best fit? No, still not, because we haven't talked anything about these projections, right? We also have to have a way of saying not only this object is better than this because there is a morphism going into it, but also these projections are better, right? So the condition for the projections are that if you go Q after N or P after N, if you go P after N, then you have to get P prime. Okay? So P after M must be equal to P prime. Q after M must be equal to Q prime. Okay? So, to summarize, C is better than C prime if there is a unique morphism M from C prime to C such that this is true. Now how do we read this, right? I mean, if this were multiplication, then you would say P prime factorizes into P times M, and Q prime factorizes into Q times M. So P prime and Q prime have a common factor, M, right? So I can like extract a common factor from P prime and Q prime. So my morphism is really special. This morphism is special. It's a unique morphism that factorizes these two projections. So it like takes the worst out of these two projections, condenses them, and then says, now you can do your nice thing and do the real projections, right? And you'll get the same result. Now, why am I saying that this is the worst thing that happens? Because if you look at different candidates, you know, it's like the Goldilocks principle. Some candidates are just too big, other candidates are just too small. They don't fit, right? And this morphism, like any other morphism, it can lose information, right? So it can shrink stuff, you know, it can project two things into one, it can squeeze, it doesn't cover the whole thing here. Like think about injections and surjections and so on. So like all this non-injectivity, non-surjectivity is concentrated in this M. This is a bad guy, right? It does all this ugly, non-injective, non-surjective stuff. And these guys have their vices too. And this guy just concentrates all these vices in one place and says, you know, P is this nice, clean projection, right? But if you add to it this ugliness, then you will get this bad projection, P prime. Okay? I'll give you examples because this is like, you know, the storytelling time. So let's pick a few. So like the real. So now let's go to programming, right? So the real product of A and B is a pair, A, B, right? The type in Haskell, this is a type. I mean, if you are a C++ programmer, then you will probably say pair of A, B. That's the type, right? In Haskell, it's just A, comma B. That's the type of pair. And we have these two functions. First, which takes a pair A, and we don't care what's this. This is like a wildcard here, and returns A. And second, takes a wildcard here. That doesn't matter. B, and returns B. Right. So it picks the first component, and this one picks the second component of a pair. And this is the real product. That's the good one. Okay? Now, let me give you some bad products. Okay? Int. Okay, no, first let me pick some two types, A and B. Just, for simplicity. Let's say A is int and B is bool. So we pick these two objects, and now we are looking at candidates, okay? So a candidate for a product, a really bad candidate is int. Right? That doesn't look like a product of int and bool at all. The product of int and bool is a pair int bool. I know that, right? This guy is bad. But it says, hey, I have projections too, right? Like, is there a function, let's call it P, that takes int and produces an int, right? Like the first here would produce an int. So, yeah, well, we can define P as identity, right? It just takes an int, returns an int. Fine. What about the second one, the Q? Okay, this guy has to take an int and return a boolean, right? Just like second here, it will return a boolean. Oh, no problem. Q equals true. Good candidate. Right? If it's my description of a good candidate, right? So the only way I can eliminate this guy from competition is say that this is better than this, right? So I have to show that there is a mapping M. So M would have to go from int, my bad candidate, to a pair of int and bool. So M of some x equals, what should it be?
X true.
X, comma, true. Right? Exactly. And now let's look at this guy. This guy is bad in the sense that it shrinks stuff, right? So this is the non-injective badness that's distilled in this guy. So this is how we know that this Q is bad, because its non-injective part is distilled in here. Okay? Let's try a different candidate. Okay? Let's try a candidate that's much. No, sorry, this is A equals int. But we want a candidate that's a richer candidate. Okay? So let's have a candidate that's a triple. Okay? So it's an int bool. So now I can define a projection from this guy to int. So I have int bool. That's my candidate. That's my C prime. And I'm projecting it into int, right? Into my first component. So this is my int here. This is my bool. This is first. This is second, right? And this is my C prime, P prime, Q prime. So this is my P prime. P prime. Okay, now P prime. Let's take P prime to be like the first component. So x blank blank equals x. So it will pick the first component. It will ignore everything else. It will pick the first component. That's a good projection. Okay. It's not unique. I mean, you can also pick the second component. There are many possibilities, right? But okay. Now this one. So this int bool into bool, right? This Q prime. This is int bool and this is bool. Well, so let's just pick, you know, ignore B equals B. So this is a nice projection too, right? It doesn't lose any information of this component. This one doesn't lose any information of this component. So they don't lose information. They don't squish anything, right? They take an integer and they give you integer. They take a bool, they give you bool, right? But this guy is too big, right, to be a product. It has redundant information. Like if I drew a picture of this, it would be like, this is a three-dimensional cube, right? Whereas my product is just a square, right? So I'm shrinking stuff. So the first one was actually covering just like one line in the product, corresponding to true and not to false. So that was non-surjective candidate. This one is non-injective because it shrinks. It identifies all the guys that have different second components. They are all mapped into the same thing, right? Okay, so sorry. So now what is the M in this case? So M would have to be a mapping from the bad candidate, which is int bool, to a good candidate, right? And again, it's very simple. It just ignores the second component, right? So it's x, y, b, and it picks x, and it picks b. Ignores y, right? So it's non-injective, right? So all these so this is very similar to what we talked about, epimorphisms and monomorphisms, except that now it's two-dimensional. So we have these flaws in our mapping. It's either non-injective or non-surjective, right? So all these candidates have some flaw, except for the good one, right? And we can always distill these flaws into this M. So finally, we can say, how do we define the product? And now I'm going to define the product using arrows and objects. I don't have to talk about sets. I don't even have to call it a Cartesian product. I'll just call it a product. Okay? Sometimes people call it categorical product. Okay? So a categorical product is an object So a categorical product of two objects A and B is a third object C with two projections P and Q. Okay, so P has to go from C to A, Q has to go from C to B. Okay, so it's this triple. It's object plus the projections, right? Which has the universal property, which means for any other object with two projections, so for any other C prime that has some P prime from C prime to A and Q prime from C prime to B, so for any other pretender, there is a unique morphism M that goes from C prime to C, which factorizes the two projections. P prime equals, what was it, P after M? P prime equals P after M, yes, P after M, and Q prime equals P after M. So that's quite a mouthful, isn't it? Yes?
Did you try M as a C prime to C? Or, because you just wrote that it's a C prime to C prime.
Oh, thank you. Yeah. But I said C, right? I just,
Yeah, sorry.
I just, yeah, okay. All right, right. It's really, I mean, I'm writing it down, but really I'm looking at the picture, right? Well, I have to change this picture again to P and Q, and this to A and B, right? But really these things, without these pictures, this stuff would be really, really impossible to remember, yeah? But you remember these pictures, these diagrams. And when I say, you know, that this is factorizing these morphisms, I mean that this diagram commutes and this diagram commutes, right? That this path is the same as this path, and here this path is the same as this path. That's commuting diagram. Commuting diagram meaning that two paths through a diagram give you the same result. Right? Yes?
So this set of things that this set of rules, is this a category?
No. This set of rules defines an object with two projections that is called now, if this is all true, then C with P and Q is called the product of A and B. So not every category has products, and even if it has, maybe it doesn't have them for every pair of objects, right? But if a category has products, then it's a nice category, just like the category of sets, because in the category of sets, every two sets have a product. So if we want to imitate the set category, we will want to have categories that have initial objects, terminal objects, products, and later we'll see also the opposite of product, which is a coproduct. But I think about coproducts we'll talk next time. Okay? That should be enough for today.